and Paula Herber on formal verification of intelligent hybrid systems modeled with Simulink and the Reinforcement Learning Toolbox. And Julius is the speaker here.
Yes, thank you very much. I'm Julius. I'm a PhD student at the Embedded Systems Group of University of Münster. And as mentioned, I'm going to present our paper, Formal Verification of Intelligent Hybrid Systems that are modeled with Simulink and the Reinforcement Learning Toolbox. This is joint work with my colleague Timm Liebrenz and my supervisor, Paula Herber. Intelligent hybrid systems are systems that combine discrete and continuous behavior, for example, discrete control decisions with continuous movement. And intelligent hybrid systems also use machine learning, for example, reinforcement learning, where intelligent components learn through interaction with their environment. These systems are increasingly being applied to more and more complex scenarios, like, for example, autonomous driving. And while they may be powerful, they are also safety critical, and failures can have catastrophic consequences, such as the loss of human lives. And because of the safety criticalness, it is important to verify their safe behavior. Which leads us to a problem. For formal verification, we require a formal system description. However, this is often not available in industrial design processes, where systems are typically modeled with only informally defined, with modeling languages with only informally defined semantics, such as Simulink. And furthermore, formal descriptions are also hard to obtain for reinforcement learning, which feature unsafe trial and error learning processes and are also often black boxes. And this raises the question how to formally verify industrial hybrid systems with reinforcement learning components. So here's our approach. First of all, we expect intelligent hybrid systems to be modeled in Simulink with the Reinforcement Learning Toolbox. Simulink is widely used in industry and enables informal but intuitive modeling of hybrid systems. And the Reinforcement Learning Toolbox enables including agents into the models and simulating them. We'd like to now verify such systems with the goal of either proving a safety property or at least receiving some counterexample to explain why a property is not fulfilled. However, to do this, we need a formal description of the overall system. And for this, we need a formal description of its embedded reinforcement learning agent. To derive a formal description of the agent, we propose to use hybrid contracts which define their safe behavior. For example, which actions are applicable under certain observations. And to ensure that the agent also exhibits the described behavior at simulation time, we apply an existing safe reinforcement learning approach based on runtime monitors, which ensure compliance with the contract. With this formal description of the embedded reinforcement learning agent, we then derive an overall formalization of the intelligent hybrid system by extending our transformation from Simulink to the differential dynamic logic to also include reinforcement learning components. And this then allows us to formally verify the hybrid system with the interactive 3D improver Chimera X. Now, before getting into our approach in more detail, I would briefly like to introduce the differential dynamic logic and our previous transformation from Simulink to DL. Differential dynamic logic is a logic for reasoning about hybrid programs. And hybrid programs are a formal modeling language for hybrid systems. They are not directly executable, but allow defining possible system behavior. So, for example, we can sequentially compose two different hybrid programs, alpha and beta. We can have a non-deterministic choice between executing any one of them. We can non-deterministically often repeat a hybrid program. We can assign values to variables and also have non-deterministic assignments. And the important thing here is that we also can have continuous evolutions where a set of variables is evolved with a set of differential equations over time, at most as long as an evolution domain F is fulfilled. Last but not least, we have tests which abort and discard a run of a hybrid program if they are not fulfilled. Now, the differential dynamic logic provides us with modal operators for reasoning about these programs. So, for example, we can define that a formula phi is true in every state reachable by alpha, or that it is true in some state reachable by alpha. And we can also write down specifications with pre and post conditions and prove these in Chimera X. To verify Simulink models, our group has developed a transformation from Simulink to the differential dynamic logic. Here on the left, you can see a simple Simulink model. Simulink is a block-based graphical modeling language that allows intuitive modeling of hybrid systems by combining blocks that have discrete or continuous behavior. And this model can be seen as a simple one-dimensional vehicle. The position here, x, is modeled by an integrator block, which integrates a velocity signal over time. And the velocity is determined by a switch here in red. And if the current position of the vehicle exceeds some stop threshold, a velocity of 0 is forwarded, so the vehicle stops, and otherwise an arbitrary input velocity is forwarded. And this model also features a zero-order hold, which discretizes the current position at discrete points in time. So the vehicle only gets momentary snapshots of its position, which sort of mimics a simple discrete controller. Now, the key idea for our transformation is to have rules for individual blocks, which are then composed into an overall hybrid program. So the integrator block is captured by continuous evolution, where x either evolves with 0 or with the input velocity, and the cases are protected by a non-deterministic choice with tests. The blue discrete block is basically captured by discrete assignments to internal variables. And we also have a global simulation loop modeled by a non-deterministic repetition of the internal hybrid program. And with this model, we can then verify properties with pre and post conditions. And we also enable contract-based verification. So we can have hybrid contracts for groups of blocks, which are verified, which then can replace this group of blocks in the transformation process instead of using individual rules. Right, for our project, we have developed a case study. This case study consists of an autonomous reinforcement learning robot in a factory setting, and the robot here in blue should reach workstations while evading moving obstacles A and B. And the environment is dynamic in that future goals are not known to the reinforcement learning robot, and that the opponents may cross paths with it. Our safety requirement here is not to crash with any of the opponents. So to always uphold a minimum distance to any of the opponents. Here we see the interiors of the reinforcement learning robot model in Simulink. This is actually part of a larger model also containing the two opponents. And this reinforcement learning robots contains the reinforcement learning agent from the Reinforcement Learning Toolbox, a simple sensor, a motor control, and an info service. And the basic idea here is that the reinforcement learning agent interacts with the environment by choosing actions, which consist of the direction to travel in and the velocity to travel with. And these are then sent to motor control, which turns them into a vector of velocities, which is then sent to integrator blocks, which continuously change the position of the robot. And for applying these actions based on current observations and reward, the reinforcement learning agent receives new rewards and hopefully learns something useful to achieve its goals to reach the workstations. And this learning process is, of course, naturally unsafe, because to learn from bad behavior, the reinforcement learning robot would first have to encounter some other opponent, crash with them. And this is, of course, something we would like to avoid. And to verify such models, we have to define some of the behavior of the reinforcement learning agent. And we do this by capturing with a hybrid contract. Now, a hybrid contract is a tuple where both phi in and phi out are also GL formulas. And phi in is an assumption of the current observations, ST, and the given system parameters, P. And phi out is a guarantee on actions also depending on the state and current parameters. And parameters, well, Simulink models can be parameterized with, for example, MATLAB workspace variables, which are treated by a transformation as symbolic constants, so that we can verify properties for every possible value, such as every possible maximum velocity of opponents. And here in our example, this is the hybrid contract we use. And just to give you an intuition, the idea is basically that the reinforcement learning agent either stops, so it forwards a velocity of 0, or if it moves with a positive velocity, this must be chosen in such a way that the reinforcement learning robot does not decrease its distance to the opponent in the next sampling step beyond some threshold, even if the opponent moves towards it. Of course, it doesn't suffice to just describe the behavior. This should also be exhibited at runtime. To ensure this, we apply a runtime monitoring approach and derive monitors directly from the contracts, which ensure compliance. The idea here is to adopt a safe reinforcement learning approach of Fulton and Platzer. Contract monitors are functions that are Boolean functions that check whether an action A is applicable in the current state S with parameters P. And these can be directly derived from hybrid contracts using the modelplex method. And then to ensure that the Simulink agent acts safely, we also use an adaptive learning method, which basically does three things. The first step, the internal knowledge basis of the reinforcement learning agent is updated. So for example, the Q value is updated based on experience gained. Then the set of all actions is filtered with the contract monitor for only safe actions. So only actions that conform to the contract. And then an action is chosen by the reinforcement learning agent from the safe set. And this ensures that the agent acts as described by the contract while the contract captures its behavior formally. And now with this formal description of the reinforcement learning agent, our goal is, of course, to formally verify the overall intelligent hybrid system. And we can now extend our Simulink to DL transformation to reinforcement learning with this formal description. The basic idea is to replace monitored reinforcement learning agents by the hybrid contracts, so by non-deterministic assignments of the actions, which are then bounded by the hybrid contract. And we also embed this in the overall hybrid program. So the monitored reinforcement learning agent does not act continuously, but only in discrete time steps. And we capture this by a non-deterministic choice protected by a clock variable. If the clock reaches the sampling time of the reinforcement learning agent, the clock is reset and the contract is newly evaluated. And otherwise, nothing happens. So the actions stay the same as before. And this clock is also evolved in the continuous evolutions. And of course, we can also transform the other parts of the system. So this reinforcement learning agent, the actions chosen by it also influence the dynamics of the system. And by transforming the X and Y integrators, we see that they evolve with the current velocity. And just to give you an impression, I know this is a bit much, but we can also replace the rest of the system with contracts, which leads to a formal description of the overall system. And also remember, this is part of a larger model also containing the two opponents. Right, and this now enables us to transform Simulink models with reinforcement learning components into DL. So we successfully did this for a case study. We then verified collision freedom for the overall model with Chimera X. The verification effort was about 20 hours for a model with size more than 700 blocks. We also successfully verified a model with 6 opponents in about 20 more minutes, which was mostly possible due to reusing already existing contracts for the opponents. And we also were able to model to verify a model with 2 opponents and disturbed sensor data. And then we also showed in simulation experience that no collisions occur when simulating the model with a monitored agent. So to summarize, our approach allows formally verifying industrial hybrid systems with reinforcement learning components. We use hybrid contracts to formally describe an agent's safe behavior, runtime monitors to enforce this behavior, and then extend our Simulink to DL transformation to reinforcement learning. This results in an automated formalization of systems modeled with Simulink and the Reinforcement Learning Toolbox. And also, we were able to verify a simple autonomous reinforcement learning robot in a factory setting with Chimera X. Now, future work consists of, for example, permissiveness of contracts. So we noticed that an AI agent that was not restricted by the contract performed slightly better than a safe agent, although it should be mentioned that this unsafe agent crashed eventually. And also automation and reuse are important topics. So we are thinking, for example, about templates for hybrid contracts to enable developers to more easily define them and verify their systems. And with this, I thank you for your attention. I'm, of course, happy to answer any questions. And while I do this, I would like to play a short video of the reinforcement learning agent moving through the factory. And you may, of course, start asking questions. So I'm done with my talk. Thank you very much.
Yes, thank you. It's question time, and I can see that Wolfgang Arendt has his hand up. Please speak up.
Yeah, hello. Thank you very much for a very nice talk. Can you hear me?
Yes, I can hear you.
Yes.
So I have two questions. One is in verifications like this with Chimera, you have a basic loop, and then when you verify that, they always need a loop invariant, which may or may not be difficult to find. Can you comment on that?
Yes, finding loop invariance is very difficult. So I think this is closely connected to actually finding contracts for reinforcement learning agents or contracts in general. And this reuse part does not just focus on contracts, but also on those loop invariants. So we could well imagine we've also, our group has also put some work into easing the process of finding loop invariants for Simulink models.
But how was it in this case? I mean, how difficult was this invariant?
Very, actually, because, well, I have to say that the overall verification effort was 20 hours for the final proof. And I think measuring the time for proofs is very difficult and actually very subjective to the one doing the proof. And in general, for this whole project, it all took a lot more time, and also finding the right invariants for different parts of the system. Sure.
Okay. Final. Is the invariant documented in the paper?
No, it's not documented in the paper, but you can find it online. The proofs are all online on our website. All
right. Thank you.
Welcome.
There is two more questions. Maybe Nayun next. Are you there? Nayun, can you hear me? Not at the moment. Maybe Andre, you can go ahead.
Sure, I'm happy to step in until Najin reaches for the unmute button. A very nice talk. I just, when you mentioned that you added what is it? You went up to 6 obstacle agents. I said, that's a lot of verification challenges and so on. So I'm very happy to hear that you ended up adding 20 minutes or so, which is terrific.
Yeah.
And in fact, you just gave me a reason that we should add distributed hybrid systems back into Chimera X to make that task easier. But maybe
I didn't quite get the last part.
I think we should add distributed hybrid systems back into Chimera to make your challenge easier there. That's completely my mistake.
That would be great. Yeah, sure.
Yeah. Anna's problem that most days only have 48 hours. It's very annoying. But can you help me understand what did you do to get that done so quickly? I'm impressed.
Well, actually, this has to do with how the proof was previously performed, and actually took a lot of care in enabling me to later replace variables of the different opponents in the proof tactic. So I had a contract for the opponent defined, which the basic idea is that the reinforcement learning robot should stop in time, and then the opponent evades. And this evasion contract for the opponent was verified for one opponent. And in our approach, we can replace multiple opponents with the same contract. And by doing this for one opponent, it was very easy by setting this up correctly to then replace in the tactic the different opponent names and enable verifying this for multiple ones. Yeah.
Thank you. Great.
Thank you.
Nayun, are you there now?
Yeah. Can you hear me now?
Yes, I can hear you.
Okay, I'm sorry. My microphone is muted. So my question is that you see whether your approach still works once we consider the state flow part, right?
Yeah, we actually are currently doing a master's thesis on including state flow into our Simulink 2DL transformation, but this is not a part of this talk because it's not really done yet, this part.
Okay, thank you.
Okay, thanks everyone. I'm afraid it's time to